Hi, and welcome to another episode from Spiral Physics Education. We're going to be looking at Newton's third law of motion in this episode, and we're going to be looking at all the rules for identifying third law pairs of forces, and then we're going to be using some examples to make sure that you understand the concept of Newton's third law and Newton's third law pairs. What would be ideal for you to get the most out of this lesson would be if you understood what scalars and vectors were and had examples of those, and it would also be good to know that there are certain forces that act at a distance and have examples of those to hand, and also that some forces require contact between two or more objects. And if you're not sure about any of those, do check out other videos on the channel to help you get up to speed on them. So let's get looking at Newton's third law of motion then. And you may have heard it in these terms before, in that every action has an equal and opposite reaction. However, that's really not going to be, let's say, scientific enough. It's more of a layman's description of what Newton's third law is. The more scientific description is obviously going to be a little bit more complicated, and it reads like this. When object A exerts a force on object B, then object B exerts a force on object A that is equal in magnitude and opposite in direction. I guess that's a more complicated way of saying every action has an equal and opposite reaction. So to give you a visual aid with that, here's object A and here's object B. Now object A is going to push down on object B and object B is going to push up on object A. So that's what Newton's third law means in a nutshell. But it's not quite as simple as that. There are rules, and they must obey all of these rules if two forces are going to be Newton's third law pairs. So they must be the same type of force. They must act on different objects. They must have the same magnitude. They must act in the opposite directions to each other, and they must act in the same plane. And if they disobey one of these rules, then they cannot be Newton's third law pairs of forces. So let's put these all together and have a look at a couple of examples. So here we've got the Earth and an astronaut orbiting the Earth. And even though this astronaut is in space, there's still going to be a force acting on them due to the Earth's gravitational pull. And that's going to pull them down. So I'm going to be very descriptive about that force. And I'm going to say to it that it is actually the gravitational pull of the Earth on the astronaut. So I'm being very descriptive about it. And it's going to help me identify the Newton's third law pair of that. Well, it's going to act up because it's got to be in the opposite direction. It's in the same plane, it's the same magnitude. And to help me identify what it is, I can rewrite that sentence, but just swap the two objects around. So now I've got the gravitational pull of the astronaut on the Earth. So the astronaut is pulling the Earth up by exactly the same force that the Earth pulls the astronaut down. Let's have a look at another slightly more complicated example. So we've got the Earth again, but this time a person standing on the Earth. So obviously the Earth is going to pull them down with gravity or gravitational pull. So the gravitational pull of the Earth on the person, just like in the last example. And the opposite force, or the Newton's third law pair force, is going to act on the Earth. And we can rewrite that sentence, but just swapping the person and the Earth around. So this time we've got the gravitational pull of the person on the Earth. So the person is still pulling the Earth up. But the person's in contact with the ground, so there must be a contact force. So that's going to be acting down as well. So I'm going to describe that as the push of the person on the Earth due to contact. And we need to try and identify the third law pair. They always come in pairs. So clearly it's going to be acting up in the opposite direction, have the same magnitude, and act on a different object. And if we want to try and be descriptive about it, we write that same sentence out, but we swap the objects around. So it would read like this: the push of the Earth on the person due to contact. So let's try another one. A little bit more complicated again. Let's say we've got a car in motion, and I'm going to give you a force and a description of a force, and each time I'm going to pause and just give you a moment to try and identify the third law pair and come up with a sentence to describe it. So here we've got a downward force, so I'm going to give you this one. That's the gravitational pull of the Earth on the car. So try and come up with a sentence to describe the third law pair of this force. Okay, so it's going to be acting up. And the sentence is going to be exactly the same sentence, but with the objects swapped around. So it's going to be the gravitational pull of the car on the earth. Let's give you another one. So this is a contact force. I'm going to describe it as the push of the car on the earth due to contact. I'm going to give you a moment to try and identify this third law pair. Well, as this one's going down, the pair must be going up, and we can rewrite the sentence but swapping the objects around. So it's the push of the earth on the car due to contact. Okay, one more. We've got this force. I'm going to describe it as the car pushing the earth back due to friction. I'll give you a moment to try and come up with identifying its third law pair. Well, as this one's going to the left, the other one's got to be going to the right. Rewrite the sentence and swap the terms around. The earth pushes the car forward due to friction. Obviously, the directions are changed as well, but you get the idea about structuring the sentence by just swapping the two objects around in them. All right, let's have a look at some more complicated questions. So here we've got a person who's pushing against the wall, and we're going to describe the motion of the wall and the person if we say that they are in equilibrium. So what I'm thinking here is that equilibrium, well, that means there's no resultant force. That means that there's no acceleration, and it means that there's constant speed, or it's stationary. So if there's no resultant force, this person is either moving at a constant speed or stationary, but it's more likely to be stationary because they're pushing against a wall. You don't normally see people and walls moving at constant speeds. So they're likely to be stationary due to Newton's first law. So let's have a look at part B of this question. Are these two forces a third law pair of forces? And we've got the green one by the hand. We're going to call that a person pushing against the wall. I'm going to call that a contact force. And the blue one, I'm going to call that a person pushing on the earth due to friction. So the question is, are these Newton's third law pairs of forces? So what I'm thinking here is, what are the rules? Well, the rules are got to be the same magnitude. Yeah, they're the same magnitude, or I've drawn them the same length. Opposite directions, yes, they do act in opposite directions. Same type of force, well, one's contact and one's friction, no. Must act in the same plane. No, they don't. One's much higher up off the ground than the other, so they're not acting in the same plane. And act on different objects. Well, yeah, they do act on different objects. However, two rules there have been broken, and therefore they are not third law pairs. So they are not the same type of force, they are not acting in the same plane, therefore they are not third law pairs. Okay, let's try part C. So identify the third law pairs to these forces. So what I'm thinking here is to identify the two objects, I rewrite the sentences and I reverse the objects in those sentences. So for that first one, with person pushes against the wall due to contact force, I swap those around. Like I say, wall pushes against the person due to a contact force, and they must act in the same plane, so acting in the opposite direction and pushing back. So that's the third law pair for that green force. So let's think about the blue force and try to identify its third law pair by applying those two rules. Well, rewrite the sentence and swap the two objects around. Earth pushes on the person due to friction, and they must act in the same plane but in opposite direction. It's got to be in that direction. Okay, so for the next one, we've got, you need to know about third law pairs for collisions as well as for objects that are in equilibrium. So here we've got a car colliding with a wall, and it's at the point of impact. So let's say we need to describe the motion of the car at the point of impact by referring to Newton's first law and second law. So what I'm thinking here is that I must make reference to Newton's first law because it says that in the question, and I must make reference to Newton's second law. It's not moving at a constant speed, and it's not stationary. It's actually decelerating. So Newton's first law, when it says moving at a constant speed or stationary, when the car hits a wall, it slows down. So it can't be Newton's first law. It decelerates, so there must be a resultant force acting on it. And if there's a resultant force acting on it, then it must be Newton's second law. So a car colliding with a wall obeys Newton's second law because of deceleration taking place. Let's have a look at part B then. So part B is going to be identifying the Newton's third law pairs to the following force. So we've got a wall pushing on the car as a contact force, and that's going off to the left. So what I'm thinking here is we need to swap the objects around in the sentence first of all. So I swap the objects around, so now we've got the car pushing on the wall, which is a contact force. And that means that it must act in the opposite direction, the same plane and a different object. Okay, let's have a look at another question then. A student makes the following observation. Students take these. Is it correct? So the student is saying that those two forces in this question, that they're the same size, they act in opposite directions, and that means that the resultant force acting on the car is zero, and that the car must be in equilibrium. So what I'm thinking about this is, well, equilibrium, it means that it's moving at a constant speed or it's stationary, means that deceleration occurs during a crash though, which that's not equilibrium. And that means that the resultant force is needed. So it's not. It sounds like it's not correct. But why isn't it correct? Well, it's definitely not in equilibrium because of the deceleration. It's but the thing is that the forces don't act on the same object. They're not both acting on the car. So the resultant force acting on the car can't be zero because one of those forces to the left is acting on the car. The other one to the right is acting on the wall. So there's no reason for those two forces to cancel each other out. So the resultant force is not zero because both forces don't act on the same car. Anyway, I hope you found that useful in getting your head around Newton's third law and third law pairs. Subscribe to the channel and check out other videos to help you improve your understanding of physics and get those grades up in time for your exams.